Good afternoon, everyone, and welcome to the DARS lecture series. It is a pleasure to introduce Alicia Nahmad Vazquez, an architectural designer, researcher, and entrepreneur focused on robotics, digital fabrication, and material practice. Her work advances the idea that technology can expand human craft, supporting more resilient and locally grounded approaches to building. She's the founder and CEO of Circular Factory, a distributed robotic timber microfactory platform, and the creator of Tierra Zen, a system of digitally fabricated cabins that bring together design, fabrication, and local skills. Over the past 15 years, Alicia has worked on projects ranging from experimental installations to full construction systems, with work realized across the Americas, Europe, and Asia. She has exhibited twice at the Venice Biennale and recently co-chaired Acadia 2024. Her award-winning project, Need Candela, has been widely recognized internationally. Alicia is an associate professor at the University of Calgary, co-directs the Laboratory for Integrative Design, and serves as a visiting professor at the Weizmann School of Design. She holds a PhD from Cardiff University and a Master's of Architecture from the Architectural Association School of Architecture. Please join me in welcoming Alicia.
Thank you. Thank you very much for the introduction, and thank you very much for the invitation to this lecture series. Thank you, Sina, also, and all the team. I'm really happy to be able to talk to your team. So yeah, I think that like as was mentioned, I want to talk a little bit about my journey today and what kind of things like we can do, or what kind of things I would like to consider for like I hope spark some ideas and some imagination about how we can design to the different future. Oops, sorry, now I have a problem. Okay, yes. So I have had the opportunity to work in different projects, like with different teams in different countries, like Mexico, Brazil, India, China, Canada, and really since early stages of my career, kind of trying to focus on how we can not only design but most importantly build in ways that could be more efficient, but also not only faster and cheaper and more efficient as maybe we are always hearing people to tell us in the industry, but also in ways that are different. And it was throughout different many years of working with different teams that really it came to my realization how by designing and building in a different way, we can also help the whole vertical and the industry grow with us, and we also spark the imagination of like construction workers, of like the trades, of like a lot of other people to kind of think different and to be excited about the future. And I think that is something that I would really like to just say, because like we try to build things and what makes us excited. I think that is the main thing, that we are now at that divergence in the possibilities of what we can do, because we know we can do it. I started working with robotics like maybe around 12 years ago. And we have done a lot of many different things with robots, and also a lot of different processes, as I'm sure like a lot of people on Asina's lab. You also do a lot of very cool and different things with robots. So a big synergy there. We also design our own machines. So sometimes we build our own tools, like a pneumatic actuator. So we also work with, if the robot cannot do what we want, we also design our own machines to do what we want. And something that is very important is, of course, to kind of think, if we are going to build with new technologies, how can the buildings and the things that we build can look accordingly to the new technologies that we have. And that is something that is very clear, like in the car industry, where we can see a big advance from like how cars used to look before to how they look now when they are building with new technologies, and with like advanced design systems and architectural geometry. However, and I think that we all know this from the built environment, actually somehow our search for efficiency and for being faster and cheaper tends to go backwards. Like we see buildings from the past and we are amazed and we are like really impressed about how they look, whereas we are kind of really building buildings of the future or our current buildings that, and I mean, and we see at least in Canada there is really like an explosion of building right now. But it's like, are they exciting us and are they bringing that sense of inspiration and awe that we used to have in the past? Whereas and that is a critical point of where we are now. And something like that is kind of very interesting is also when we look at construction systems, and we look at like the rebars or like reinforced concrete, we see that these are patents that have been existing since the 1866, 1900s, and that we still build in the same way. There is a very like we still use all of these systems. So how can we really make our work and our research with robotics and with new builds of technique kind of mean something, and why the industry kind of is not moving in these directions? And maybe we hear a lot now we hear a lot more about like timber and CLT, but if we look at the patent of CLT, it's also from 1920, so it's more than 106 years old by now, that this patent. So it's also not the super new construction method or that we are imagining. So how can we bring these tools to actually build in ways that are different? Oops, sorry. And we know, and it's kind of interesting because a lot of the presentations that I see and I go, I mean, like everyone, like AI can give us really good ideas, and you see all of these presentations also like from developers, and like they end up with like we can do all of these, and then at the end there is an AI image, right, which looks totally different to what they have shown you for the last 20 slides. Now we know that it can really give us really good ideas, and it's really fascinating era that we are today, where like a lot of people are starting to imagine really different futures and different realities for the built environment. And for me, it's always exciting when someone kind of even shows us an image and I'm like, okay, more people are starting to think that we can build different. But what we can actually do is, how do we build them? And still it's very important to think, okay, we have all of these ideas. How can we manufacture them? How can we build them? And that's where our work has been situated for the last kind of years. It's like in how do we build these things? Of course, and thankfully, as we like, and this is not something like super old, but more recent, like technology has really become more accessible. Like we can have access to a lot of more, not only robotics, also a lot of more like computer vision tools, a lot of more algorithms, a lot of more like machine learning right now. So a lot like a computing power. A lot of this is becoming so much more accessible that is such an exciting era for where we are right now as architects. And we also know that if we want to build differently, we want to look at new construction realities, a lot of that is inspired on the past, right? So we have to look at old rules of building, ancient rule geometry, form finding, thin shells. All of these give us an idea of how we can now build in this, like use like maybe techniques that became discontinued because they were too expensive, too difficult, because maybe the master builders disappeared. We can now redo them using robotics and digital fabrication. So we know that a lot of this is coming from the past to now learn of how we can reinterpret some of these rules and build in a different way. So it's really, we kind of have all the ingredients there. We have the rules from the past, architectural geometry as a field that has advanced so much. We have technology. So it's really about we as architects, how do we use them and how do we build and how can we imagine other possibilities? How can we use all the advanced technological developments that we have for new build realities and for a build environment that kind of excites us? And something very interesting, we don't really need so many new technologies, but when you think of, for example, and this is like a light bulb, right? Very simple light bulb, the most common, maybe a very innovative part of technology when it came out, and that really changed the way we live and what we can do, but very simple. And you normally will see a light bulb like this, like on a street lamp. But then this is like an installation that Olafur Eliasson made at the Tate Modern. This is all using only light bulbs. Like that very simple piece of technology, super boring, nothing exciting, but it's about how we use them. And it was like, I mean, this was one of the most beautiful things you could see. Like you will see people sunbathing under the sun. It just really like, wow, will like blow your mind to see something like this without an advanced technology. So the reality is not about if we have the technologies, it's about how we use them and how we can imagine with them. And we have my practice or my work, we're always driven by technological optimism, by really kind of thinking technology is good, is something that we should embrace, we should use if we want to have more diversity, more equity, but also a more efficient and sustainable built environment. So some of the first project that we started doing was like this shell learning from Candela, which we built a couple of quite a few years ago now in Mexico. And this was kind of, we only had a CNC at the time, like we didn't have robotics or anything like that. We kind of designed this shell. All of the arches are like single curve, not only one is like double curve. Everything was done with like craftsmen at the time, like masons, right? That they were like bending the beams on the edges. And the formwork was all kind of done just with like a CNC machine that we had on site, and like we did this really sparse formwork, and then on top of that, the concrete builders, they kind of rendered the concrete 6 centimeters thick on both sides of the shell, and then you can see the rebar. Something very fascinating was to see the rebar distribution, how it really kind of starts to match to the design and the topology that we had on the poly modeling software, right? So it was a really kind of seeing how we model also can represent how we build. Then we also have explored like a topology optimization. How can we reduce as much material as possible from a shell and still make it efficient? So a few years later, we built this shell collaboration with Chrysler Associates. And Saha Code and Odico, and kind of really trying we first designed the shell, remove as much material, and then building the formwork. In this case, was a bit of a more complex formwork, but still just using a CNC machine. And a lot of the workers will tell us, you know what, we don't really need any more than just a guide. We don't really need you to tell us how the shape is. So it started to become really interesting for me to understand how we can merge these very skilled craft people with actually technology, because they only needed the formwork as a guideline, as a reference. Based on that, they could build this shell, which was rather complex, still standing, maybe like more than 13 years later. It's still in Mexico City after quite a few earthquakes. So really a really nice proof of concept. Then we also explored more of topology optimization. How can we build this kind of using different materials? So this is another shell that we built. With that fan is a kind of a fiberglass manufacturer in Dubai that we built for like the Seoul exhibition, trying to see how can we make the molds, how can we use digital fabrication robotics to make the molds, to make it more efficient, to kind of build shapes that maybe are slightly more complex. And after this, like in 2018, I was invited to collaborate with the Block Research Group and Saga did Architects Code to build Knit Candela, which it was like a very innovative shell in like Mexico City. I mean, based on all the previous experience that we had at this time of building shells, and this was a really interesting experience into like how can we bring the really advanced technology at the time being developed by the Block Research Group in the terms of like a knitting formwork, right? On a knitted formwork, which basically was going to be a stain in place. So it was different from our previous formwork exercises, where we already were capable of reducing quite a bit the formwork, but we still had it there into a really kind of stay in place knit. For this case, also we had to work with like a really kind of hierarchical utilization of technologies, where we knew that the knit required from a very precise localization of the stretching points, right, where it will be stretched, just to make sure that when it form finds the correct shape. So, but we didn't have access to really sophisticated machines. At this stage, we still only had the same CNC that we have been having every time we go to Mexico. So we kind of really had to work through like a lot of different iterations into how can we decide which parts of the geometry are done with the CNC to be super precise, and that really will kind of dictate and lead how the fabric gets extended, and which parts of the geometry we could have a little bit of more tolerance for the workers to do manually. So it was really a lot of discussions also into not only the precision for the hierarchy, because we know that not everything needs to be done by robots or by digital, but there is how can we merge these two worlds together of digital fabrication and traditional construction. And finally, we build the scaffolding. We build all of that big scaffolding that you can see out of like timber 4x4s with lace CNC lumber inside to really mark the correct spots where all the hook rings will come, to then finally when the fabric came from Switzerland, it got just like assembled in place and stretched, right? And we didn't really scan it to make 100% sure that it was the correct geometry, but it stood there for a long time. They didn't look terribly wrong. So we kind of it was a really exciting step for us after working through like many different shells, when actually we really needed these high degrees of precision to understand how we can mediate between these. And at the end, the shell was rendered in concrete by the same workers that have already been working with me on all of the previous shells. And something really exciting that happened to me when I called the workers to build Knit Candela. This was like the third shell we were doing, right? And a lot of them were actually telling me that since they started doing the shells, they show this to like any other contractor. They go to work with, like, hey, I have built this, and that they kind of really can enable them to get other jobs, but also to see that pride in their job, right? To create that pride in the workers of what they are doing is something that like really makes us think, well, how can we, like the construction is a vertical, right? We need to integrate with the trades, with the designers, with contractors, with developers, with architects. So seeing that actually it's benefiting, the fact that we are doing different geometries is benefiting everyone, and it's making them really excited, and everyone got paid all the time, overtime. Everyone that worked overtime got paid, but the workers were working overtime, and they were kind of really excited, telling us like this is one of the most like exciting projects we have worked on for a very long time. So it was really fascinating experience. And of course, it kind of makes us think, how can we change how we design and how we build, and how can we incorporate architectural geometry and fabrication machines, and also enhance this stakeholder participation, not only developers, designers, clients, architects, fabricators, but also the masons, the workers, everyone on the vertical of construction, enhance their participation through technology and through different ways of building and changing. And like we have been looking a lot at like our robotics as that flexible machine that enable us to do like hot wire cutting, 3D printing, milling, like sand cutting, like all kinds of different processes, right? So we know that we have a really small, compact, and affordable, powerful machine. And these are some of the projects that this is a project we developed at the AA, at the DRL, in collaboration with OGCO. And trying to look how can we make these formworks to kind of create different, like this was a mock-up for like a 1-bedroom flat with one of our OICOs, one of our teams at the DRL. How can we also use the robotics to create patterning, to create these spaces that maybe the ornamentation is part of the design, but also how can it mix with traditional ways of building? So not everything was robotically fabricated, but we have a very traditional stick frame construction that kind of merges with these new ways of building. And this was something that we proposed to the building minister at the UK, kind of how can, and they were really excited as the fact of like we are merging these two worlds together, right? And more importantly, this was some of the early experiments also at the DRL into like clay printing, into developing our own kind of extruders in collaboration with the build space at Autodesk. But the more important thing was not only 3D printing, but also what are the new built realities that this can bring to us, and the new spaces that it makes possible. So we were always kind of trying to work in between these two worlds. And like if we have a wall that is 3D printed, can it also enable like for infrastructure, like installations? How can it be different from just a normal wall that is normally like a stick frame construction, right? With a wall, like how can we really take advantage of all of these technologies towards new topologies and new tectonics that maybe were not possible before? And so we know that robotics and machines in architecture is not something new, or in construction. We have DFMA since the 1980s, design for manufacturing and assembly, but we do know that it has led that it kind of factory-made buildings are not have a lot of problems that we don't really see on buildings that are built on site. Although they are faster, efficient, and sometimes maybe cheaper to do, they do rely in pretty much centralized supply chains. They require from transport, and they don't always adapt to local economies because they don't need to, right? They are made on a factory offsite, really far away. So they don't connect a lot with not only local economies. They don't benefit the local economy, but also with maybe local idiosyncrasies, local ideas of what they like. It also tends to be expensive just because of the capital cost related to the machines, to the robots, to the knowledge. And so it lacks kind of ornamentation. And we know that robotics can give us all of this ornamentation almost for free. We don't really need to put any extras, but we are missing that integration with the local ways of thinking, local crafts, local skills, local supply chains, and still in the world that we live. Small medium companies are like 98% of the contracting firms, and not also as developers. We also see a lot of more small medium developers that are doing like infill housing, small like maybe duplexes, quadruplex, like 4 or 5 story buildings as a response to the housing crisis that we have around the world. We see that it's not only about the big developers that could maybe afford this, but it's about more like small medium companies that need new ways of thinking, new machinic ways, and new ways of building. So something that we have been thinking is, how can we move from this DFMA from the 80s into a paradigm of like design for robofacturing, of like using robotic cells that can robofacture high quality products and can be in a not exactly on site but near site, can integrate with local supply chains, can integrate with local crafts, can integrate with local economies, and kind of this is where we have been working when we refer to like small. And why we like about robotics is, of course, because we can do like scanning, milling, assembling, 3D printing. So we have single machines, multiple processes. There are, of course, and we know there are like maybe some trade-offs in accuracies and efficiencies, but we do kind of have a very, very simple way of doing it. When we talk about flexible robot cells, we don't talk exactly about a container. We talk more about kind of just robotics that we can develop in we're talking about a 250 square meter maybe facilities what we have been developing, where robots can have different configurations based on like different production lines that are required by our like different clients, and also by the different products that they are looking to produce. We know, as I mentioned before, we do know that it's not only about the robots, it's about the general like other machines, woodworking machines, metalworking machines, storage spaces. It's quite a lot more to that. And of course, really benefiting local economy, not only by incorporating the on-site trades, but by buying materials that are local and local supply chains. So that's kind of the work we have been doing, like this DFMA to DFR. And that's the work like I have been developing more closely, especially over the last 5 years, into like architectural geometry and trying to democratize the digitization of the construction industry to a larger public, right? To be able to engage more people we need. And also we have been working on developing these participatory frameworks, like to engage more stakeholders. So as part of design for robofacturing, we are working in a machine information, in developing cyber physical platforms, and that's part of the work we are doing here at the lab and laboratory for integrative design, into how can we keep these limited resources but introduce new vocabularies in this context of design for small robot cells for robofacturing. So one of the biggest changes is architects as system designers, as a system designer that control the process and controls the technology. So this is a retrofit for a building of a facade, as a facade of a building, a retrofit that we were working on. In this case, the building already exists, and we kind of designed this. It's all like catenary curves that are bent glue lamps with like different apertures depending on the sun exposure, but not only from the outside, also from the inside, of the view that the people wants to have, of the street view that they have, of their relationship to the outside buildings, and of the solar gains and energy gains. So in this case, we kind of did all the studies on, like you can see, from exterior solar gains, but also from the interior, different views and different transparency levels that the facade could have. And then there's a work, it was the participatory framework, where also we can have the people that are living or occupying the building, the occupants, kind of being able to decide, and to, in this case, like using a gaming engine, being able to decide how they want this facade to be, like more out, more in, but at the same time, giving them feedback of like, well, that this will, you have better views, but less on exposure, or more radiation, or you are going to have more energy consumption. So like they could pick between transparent and opaque panels, and they could pick between pushing the facade further out or more in. And the idea is also that the final user, the same way that when you kind of buy food on the supermarket and you can see the nutritional ingredients, right? You could also get an idea of like, well, if I do these design changes, how is the energy consumption changing? And we eventually want to integrate this to fabrication, so that we can say also, well, this will require more material, right? So that we can have a really clean and clear and transparent bill of materials and understanding of how these small decisions affect the whole downstream production cycle, not only the use and the occupancy, but do you maybe for a little changes on the geometry will kind of require a lot of more wood, right? Of course, on the back end of the platform, there is all the solar analysis, like all of these like different configurations, and also like we had on the back end, it was constraining to, okay, what is the acceptable range? How much can this move? When the geometry starts to be invalid for the robotic, for the catenary curves, for the bending of the glue lamp, all of this was calculated on the back end, not available to the user to see. But kind of was a lot of the smartness on the platform at the back, right? And this was developed at the lab by one of my PhD students, also Arman, working on this. And this was like all of the structural analysis also, or like how the different configurations that the user is picking, whether they are working or not, when they start to be one next to the other, right? It's not a single node, but multiple nodes. In this case, the project was a collaboration with Dialogue Architects and also a local facade fabricator that was very engaged in making this facade with us. We did prototype quite a bit of these nodes. So all of these are catenary curves, so they could be easily bent on the glue lamp laminations, could just be like kind of glued together, then bent, and then again using the same robotic setup after bending to like do all of the slot milling and all of the kind of all of the holes, all of the drilling for it to be kind of to be assembled on site. So it was looking at the full this geometry and fabrication feedback was put back into the platform to like kind of know which ones of these geometries are feasible, which ones are not feasible. So integrating all of that knowledge back into the user, not only from a geometrical view, but from a fabrication standpoint, and trying to make this as transparent as possible all the time, right? So here we had this one, the miters. Okay, yeah, we had all the slot milling, and then all the miter cuts on the ends with the circular blade, and also with the spindles. So and then again, same machine, multiple different processes. And well, this was the kind of prototype. These are the nodes that were done, the steel nodes by our facade partners, and then some of the prototypes of the facade that were finally fabricated. But the more interesting thing was all the participatory design framework that was developed with our students. Other part of work that we work is towards like these heterogeneous material understandings. Like now that we know we have digital tools, we have computer vision, how can we look at material not only as timber or like glue lamp, but how can we actually see what is inside that glue lamp, and how can we make it smarter and have more control over the material? So this is a project that we built in here at the University of Calgary, also in collaboration with ZHA Code, into looking at different glue lamp, bent glue lamp expression, right? And in this case, as you like, the idea was on the bottom, the glue, there is a thicker lamination, right? You have like maybe 8 to 12 lamps. As you go up, you start to reduce 6, 5, 6, 4, 2, and then at the end, you have only a single lamination, right? So making this glue lamp being very expressive into the structure, and not only as something that you kind of buy. In this case, we had to develop our own machine, which is all linear actuators that kind of have a speed. So based on the speed, you can control how far they go. The speed and the distance gives you control over the actuator. And then we had the different curves. In this case, these are not catenary curves. There is a lot of different curvature. So we had to kind of work with our own machine and really try to explore that hierarchy from the bottom to the top on the bending and on the curvature and on the material affordances. And so we also started to explore at the same time what happened if we start to like mix different woods. So for example, we have walnut or a harder wood on the outside, which will be more resistance to the weather, will be a lot more strong. But then in the inside, we do have kind of like softer woods that will make the lamination at the end of the day kind of lighter weight and not as heavy. And this is something that we also explored a lot at my studio on the M.Arch at the Wisman School of Design, that kind of these hybrid laminations from like kind of, can we do laminations in these cases from one of the teams with like pine, Douglas fir, oak, changing the lamination, and what are the implications that this eventually could have not only for the aesthetics but also for the performance. And we have done this work. In this case, this is walnut, again with pine, and again with like Douglas fir, trying to see how can we also maybe use the more expensive woods to the harder ones where we need that resistance, and also on our interior laminations. And we also are looking at machine learning as a way of understanding materials, right? So not only identifying wood, but also what are the wood imperfections, where are the knots, what is the direction of the grain, and how this can help us to have a more efficient workflows for like towards milling or towards positioning our wood on the machine, so we know that we are not only having the most efficient wood, but also that we can control the speed of the spindle, especially when you are milling curvature, that you can control the speeds as you go from the directions across the grain to align to the direction of the grain. How can you actually work with that? And this is a lot of the research that we have also been doing. And we kind of also look at how can we disseminate this technology, how can we bring these machines a little bit in the wild. And some of the work that we have done is also in this like kind of robotic container, basically, where we have two small UR robots, and this is more like kind of really engaging the further public, trying to like schools, post-secondaries, but also just like the broader public with robotics. And we also get like people get super excited maybe about things that we think are normal, but they get really excited. And some of the advantages that we also want to see in this case is, well, like if we are bringing robots, like for example, in this case, it was more like to be drawing and to making an engagement exercise, but also when we are building volumetric stuff, in this case, this is a curb crease folding benches that we did for the city. This is all just aluminum, like very thin aluminum. So we know that we can just like score them, then we fold them, then you get the bench. However, it's very easy to move aluminum sheets around. They are flat. When they are folded, they are they use a lot of space. The volume is really high. So can we just bring the robot inside the container on site, and we just score all of these, and then we can build them, and then we can just bend them on place and have the benches. So this is some of the furniture that it's just a small scale, but that we are doing with that strategy. And some of the other work is also kind of related to what can we do with concrete, right? So this is a concrete battery, storage battery, but it's also a bench. In this case, all of the form work was also hot wire cut using robotics, and then trying to think, if we are using concrete and we know we need to use concrete, can we do something a bit smarter than just like making it full of concrete? And if we do topology optimization, what can we do on those spaces, right? So in this case, we had sand batteries inside, and we had a thermostat. So in the winter, when you sit on the bench, it will just warm up and you will feel a bit warmer. And so this is some of the work that we kind of are, some of the research that we are kind of looking at, always trying to think, what is exciting about these materials and these machines, and how can we make it different, or how can we make it more efficient? Maybe not always in the ways that is just making it simpler, but also making use of the concrete in ways that could have alternative, could do more than just being a bench, right? So we kind of really use how we can leverage technology to really create this sophisticated, dynamic, and customizable process. And more important, imagining a different way of building, imagining a different way of relating to the trades, imagining a different way of how our buildings look. And And I think that this is a phrase I read kind of a couple of years ago, but I really like it, from Francis Kere, of like, the more local materials you use, the better you can promote the local economy and build local knowledge, which makes people proud. And this is so true and so related to our experience, and that it's really kind of really motivational to us. So like maybe like 5 years ago, we kind of started the Circular Factory, which is like a startup. It's a small micro factory. It's maybe like 400 square meters with robots, and we have been exploring that. Like a lot of different ways of building. We have really been like mainly using local timber. Even like in this case was the most extreme. This is a project we did in collaboration with IAC. The students came to our shop, and basically we like used local discarded tree forks, and then like scanning them and designing the joinery, and then based on that milling all the connections, and then we kind of did this pavilion to kind of really, this was really engaging with the wood that was just like next to us, right? But the main idea of the Circular Factory was, we were kind of how can we build something like super nice, right, and really beautiful. And this is a collaboration again with did ZHA Code, and like they were going to build this project, and how can we build it on with local resources and not like importing everything from abroad, right? And the idea was the same as I mentioned before. How can we engage with the local material suppliers and with the local economy? So with this idea, we kind of started to design the microfactory. Of course, this being a Hadid project, it had all the complexities of a configurator. So it really had a lot. So it was giving the users a lot of different options, like they could pick their windows, balconies, and we had to design a factory or a production line that could have the flexibility, because we don't know what the users will pick, right? So the flexibility to produce all of these different components in an efficient way. This was a really kind of exciting collaboration that we had. And all the configurator, all of this was done by Zadit. And they had like this very large kit of parts. And so some of the first steps that we kind of really had to think is, well, how can we work with like these certified forests, or really kind of try to look at raw materials at the local, what is locally available. We were not sure what was locally available, and then try to create this local microfactory that could integrate all of our experience, the digital information, and the local knowledge of timber, which was not a lot, and also create these components and this kit of parts for these modules. So one of the first things we had to do was really a hierarchical analysis, again, like in Candela, a hierarchical analysis of the pieces, right? Like what requires more curvature, what is the more sophisticated parts that actually need from digital fabrication, what are the parts that could be maybe done more traditionally, and how we can split these to kind of really have like an efficient factory. Of course, we designed all of those panels, like with their corresponding fabrication process, like planar, jointer, robotic CNC. As I mentioned, it's not only about robots; it's about the full production. And having inside each panel, you had all the pipes, the insulation, everything that you really need in a construction project, right? And then we had all of those curved modules. What do they need? And how can we make them? They ended up being made with the robots, not in this way. So we kind of work in rationalizing and doing the DFMA for that complex design. Something also interesting that we had to take into consideration was the fact that there are no cranes. So like, for example, we had to see, okay, what is the biggest machine that you have? Well, it's a telehandler. It can only carry 2 tons. So we have to make each component, regardless of what the robot can do, to not be heavier than what the machines can carry, right? So really trying to localize everything from production materials to the local machines and the local existing facilities. So you can see that all the panelization is made in small panels that can be carried. We look at the lamination, how can different lamination techniques, really going back to that research of like the grain directions, like merging different lumbers, how can this give a different effect at the end, and actually a different aesthetics that we can actually control, so we can control the direction of our laminations. And we built this first prototype at the Hook Park in London on like kind of just testing some of the ideas. And then based on like, this is a Hook Park, right? Like bandsawing, the milling, the prototype, like based on that circular, like we thought, okay, this makes sense. We can really kind of dive into this and start to do that microfactory adapted to the local means. So the design was really trying to keep the footprint as compact as possible, but having all the machines needed, all the storage, and all the different utilities. As you can see, material comes in, gets processed, you have a crane, you have a storage, assembled, then it kind of gets out, and trying to really minimize the financial investment while maximizing the flexibility and the ability of making different things. We also have a lot of computer vision to understand when, like, how to adapt to local materials that might not be precise, might not be totally correct, right? Might have some deviations. And also really trying to engage fabrication, assembly, also the designers, like the designers have a lot of access to the platform, and also all the shop, all the factory floor in logistics cost, time, data analysis. And all of our machines. So we work in integrating all of the machines on the same data workflow to have everything connected on the shop so that people on the floor can be continuously looking at the screens, looking what to do, what's going on, what is the bill of materials, what machine they need to use, what parts they need to process. I mean, it's like thousands of different pieces, thousands of different parts. So it really, how can we better manage this complexity to be able to produce a project that requires from this level of sophistication. So in this case, you can see from the mesh to the rationalization into those pieces that could be dealt with the local machines and with the design that we were putting, not only of the how the machines are located, but what is the interaction between them, what is the production pipeline and the workflows between them, and then looking at the different lamination strategies that we could use, right, 2D, 3D, to also be the most efficient as possible with the material usage, but also the most efficient possible with the machine usage, with our electricity and the glue. I mean, you have all the other different things that you kind of have to consider. So all of these pieces get like 2D milled before being kind of assembled, and then being finally 3D not 3D mill actually, but 5-axis milled with the robot to get all of those complex curvature and complex shapes that were required. So this is kind of a lot of the work that we do on our platform, that we have our own bespoke, like kind of developed platform to kind of do all of these processes. Also, of course, you can see like all of the different machines, right? Like really kind of try to look into what machine is there, what is in a single given day, what is programmed, depending on the piece, what does the people working on the floor has to bring to the machine, how many boards, which is the size, and also they need to be able to visualize what is going to go on those boards. So we're trying to, so in this case, we're trying to integrate in our platform from the designer mesh to like the shop worker, kind of the whole process, right? So they can see what is going on, and they can also localize like the different pieces. Okay, like they can see not only where does it go, but they can also like understand what part of the I mean, what part of the how it is tagged, basically, how is this how is it referenced, and also oh, this should be, yeah, and also what kind of materials they need. So this is also communicated to the developer and communicated to the architect, right? So this piece, this is the identity, is located in this part of the building. It will need a certain amount of materials, including like a wood, adhesives, brackets, how many hours it will take, not only machine time, which we know is really easy to calculate because you just like simulate it, but also human time, right? Like humans moving stuff around, humans loading machines, all of that has to be calculated to have an accurate time of how you can make these. And with a lot of these human processes, is really, they are not really quantified or digitized. So that's a lot of the work that we look into, and also a lot of the unsupervised time, which basically means that the piece is in storage, or the pieces or the glue is drying, right? How many people you need, and for example, sanding, staining. So all of this, trying to quantify all of this as much as possible, so we can have a reality of what does it mean to build these projects, and we can communicate this to all of our partners, like the designers, the architects, the developers, and also the contractor who is actually building on the site. And of course, keep scheduling things, right? Like how things get scheduled, get constantly rescheduled. If there is an error, if there is a mistake in a piece, well, then it has to be redone. But of course, it's not as easy as I have to redo it. There are a lot of processes before and after that have to be dealt with. So this is a lot. So in this case, like a person, you can put where there is an error or it was actually finished, and then things have to be constantly dynamically kind of changed. So this is like how our shop looks. The first Secret Factory 1 has the robot arms, two large robot arms on a truck, and a bunch of other machines while everything is processed. And where we are really kind of have 20 people, all of them local, that have been trained for a couple of years now, and they started, maybe some of them had a few, some like minimal carpentry knowledge, a lot of, and like at least 5 of them are now using robotics, and some of them even programming robots and programming CNC machines like in 3 years, right? So I think it's pretty amazing, the learning curve, and also how they are happy to actually be learning and doing new things. And this is a prototype that we built of that Deja Vu project that we exhibited in 2023 at the Palazzo Mora in the Biennale, where we kind of built all of this using our platform. We also look at patterning and different techniques. And on the more lately project, we have developed a kit of parts for a prefabricated glamping cabins, all of them using timber joinery, traditional Japanese joinery. So all of this means that all of them can be assembled, disassembled, and with a really interesting kit of parts where you have a kind of not only timber frames, but also like kind of facade panels, facade louvers that have a different gradients, so people can really pick what do they want in terms of like finishes, in terms of facades, in terms of the wall panels, but everything is done using joinery. So it's actually, it could be disassembled, moved to a different place, different to like a stick frame construction. So here you can see some of like the panels that we have on our kit of parts, different panels. Everything gets very quickly assembled on site after being prefabricated cabins. And yeah, these are some of the cabins that we have built. Well, this is the same one that we have built actually on site, with like kind of all of these interiors, all of them like really trying to be kind of organic and trying to take advantage of the fact that we have digital tools to make something that looks and feels different, and that kind of gets people excited. And when they get in, they really feel like this is a space that is different, but it's still using local machines, local materials, local workers, local crafts, and producing near site all of it. So these are some of the interiors of the cabins, and yeah, and that's our work and research. And thank you very much for this invitation, and I hope I'm on time.
Hello, hi. Very
Hello.
so very interesting presentation on projects, honestly, and very impressive. I have a question about the one that the project that you used hot wire cutting and then using it as a formwork for concrete. If I remember, so you had really delicate lines, but however, the quality of the concrete was really amazing. And I've been there like pouring concrete, casting, and then being able to handle those like really delicate lines is a bit of a tricky job to do. So I was wondering, like, could you share your experience more on that, on type of like using formwork for concrete?
Yeah, so that's something we have been working on for quite a lot, especially because a lot of our industry partners, they want the formwork, right? So we have tried a lot of different solutions to code the foam, and also to enable them to get like the creases that we want, but also to enable them to demold, right? So that's a lot of our conversations with our partners of where do they need like the holes to demold, and also like we use a lot of different products to coat the foam, like from chalk liner to latex to like really kind of special paint. So yeah, so that's a lot of iterations. We have done a few of those projects of preparing formwork for concrete casting, and I fully understand the challenge. I think that we have found different products that kind of really help you to coat the foam and enable to keep the resolution of your creases and whatever features you have, and then could enable the concrete to be demolded. So we have found a lot of few products, the more important one being chalk liner.
Okay, Alicia, I have a small question. When it comes like to working with wood and the raw elements that you use for the pavilion, how do you deal with the moisture level inside of these elements?
The logs.
Yes.
Yeah. So the logs, I mean, they are huge, right? So they are green and we cut them. So like there's really, because I mean, it's like green wood and it's drying already assembled in place. So it's just drying on the shape it already has. We didn't, that pavilion has been up already like for 2 years. We have not, I mean, we have had to adjust it a little bit, like just tighten it, but it's drying as it is. These are really big logs. And one of the main problems that we had with that kind of raw wood was more related to termites than to actually the raw material. So it had to be treated eventually, and we had to cut it a little bit and clean it up. But especially being on a tropical place, those are kind of the bigger problems that you will find. But yes, the fact that is that for all of our projects we do use dry wood. We need to have really dry wood, otherwise we cannot really deal with the expansions. Well, we cannot really with gluing. Nothing will work, right? So we do buy treated wood, and we do have it at 8% humidity level normally, except for the logs. But those are really big logs, so they are happily living. They are already assembled, drying on site, so it really doesn't. I mean, they expand and contract with the dampness together, right? So I think the fact that they are already locked together enables them to just kind of keep moving. All the joints have a gap, and they all have bolts, right, to enable them to keep continuously working without blowing.
Thank you so much.
Hi, I really enjoyed y'all's work on those like creation of those modules that you kind of scaled up into larger projects. So do you? Oh, I need to speak loud. So you have any advice or best practices for creating modules that scale at a in a good way? So,
What do you mean modules at the scale? I'm sorry. If you can explain a bit.
so the project that you worked on with the Zara Hadid architects, where it was the creation of that large scale project that was made of multiple modules that could be arranged in different ways, and then the other one where you're talking about the factory that y'all are designing for the for your like robotics work, where you guys create these different modules that allow different arrangements of these robots within those spaces. I was wondering if you had any advice for creating those spaces or best practices for that kind of stuff.
The spaces in between?
No, like the spaces themselves, like how to create spaces that connect and scale well with one another and still create these modular areas. So.
Yeah, I mean, I think that for us, like as I like we kind of really have this like the size of every module in this case was mainly dictated by the size of the machine that will carry them. We have designed other microfactories for other, or we are in the process of designing other microfactories for other locations, which have different constraints. Like maybe it's not that they don't have cranes, but they don't have space, or the spaces are different. So something that we really appreciate about the robotics and the kind of parametric tools, right, is that we can adapt these to like I mean in our case, like for the layout of the machines, it's really important to actually know where material is coming from, how it is going to exit, how it is going to go through every single process, and you need to kind of work like for example, if we had like 16-foot long like roofs as we had at the beginning, the length of the factory was really different, because now we know that you have to take out these like super long beams, have to kind of get out of the factory, right? So we had a more of a different linear configuration, thinking that really long elements are going to come in and out. But then when we realize we don't have a crane to carry these super long elements, we have to change to more compact elements. So then we have an access where you actually can go around and actually reduce the footprint, right? So you always want to have a clear entrance and exit of your materials. And as they go through the process, if you have a large beam, you're not going to be twisting corners, right? So that is kind of, so how we start to design is by, design the microfactories is by really kind of looking at available machines, and then based on that, available materials, dimensioning, okay, what is the size of the panels, how long can we go, how big can we go, and then based on that we have maybe a more square configuration, more rectangular, more elongated, and then the machines, the robots, like I mean, we do have a few of we do have some big robots there, but some of the other micro factories we can do like a 4,600. We kind of design smaller robots. So it's basically defined by what are the machines around and what is the local material, and then we can rationalize any geometry to that. I mean, then we have joinery connections and all of that, right? So it definitely is a really, it doesn't really scale. Like if suddenly now you come to my shop to a CF1 and you say, hey, I want to make a 16-foot beam for the ceilings, it will be, I will say, well, I have to change my machines. And we design that, like, okay, now we need to change the configuration of the machines so it can get out, because with the current configuration, it will get stuck. So these are the kind of things that we do keep in mind to design, but that are very important for the layout. I don't know if, yeah.
Okay, I believe that that's it. Thank you so much, Alicia, again, for having time to share with us your amazing work.
Well, thank you so much for the invitation, and have a nice weekend.
Thank you, guys.
Bye, ciao.